Welcome back to the online lectures, and we are already halfway into the semester, right? So this is the 9th week. And how are you enjoying this flipped classroom style lecture? I hope you like it. Okay, and from this week, as you can see, I have changed the format of the lecture slide. So now it's in the wide format, so I hope it will look better on your mobile devices and also on your notebook computers. Okay, so the chapter that we are going to study this week is chapter 30. The title is Induction and Inductance. So far in this semester, we have studied the electricity and also magnetism, right? So we first learned the electric field, and we also learned the magnetic field coming from the electric current, right? And this already gave us a good idea that the electricity and magnetism are closely related to each other. And from now on, we will study the connection between the electric field and magnetic field in a better detail. Okay. So in this lecture, we will first study that the electric field can be induced by a changing magnetic field. And this phenomenon is called the induction. Okay. And in doing so, we will learn two laws. First, the Faraday's law and also the Lenz's law. And we will also learn something called the inductance. And we will also learn the device called the inductor. So inductor is a device that will have an inductance. And we will also learn how the electric current behaves when the inductors are involved. Okay. And finally, we will learn that the energy can be stored in the form of a magnetic field. Okay. So, in order to study the magnetic induction, we will first perform a simulated experiment, just like as we have done many times. Okay, here we have a permanent magnet, and then here we have a coil which is attached to the light bulb. And we will see what happens when we use this magnet around this coil. Okay, should the light come on? Okay, we will see that. By now, I hope you have a good idea about the magnetic field around this bar magnet, right? So it will come out from the North Pole and come into the South Pole. And then the strength of the magnetic field will be stronger around the magnet, and it will be weaker when you are far away from the magnet, right? Okay. So even though it's not visualized, certainly there should be some magnetic field around here too, right? But then nothing is actually happening in the coil or in this light bulb, right? So certainly magnetic field itself is not really doing much. But then let's see what will happen if I move this magnet around this coil. Okay, can you see? So when I'm moving this magnet around this coil, certainly the electrons are moving, which means the current is flowing. And this light is coming out from the light bulb. So it apparently shows that this current appears only if there is a relative motion between the magnet and the loop. I mean the relative motion because it also works when I move this coil around the magnet, right? It's actually same thing is happening. And then now let's try a little bit more systematic observation. So first I will try to move the magnet slowly, and then later I will move the magnet fast. So let's do it first slowly. So when I move this magnet slowly, as you can see, the current is coming out, but and then okay, the light is coming out, but it's very weak, right? But in contrast, I will move it fast this time. Okay, so I'm moving about the same distance, but as you can see, when I move it faster, the light is coming out stronger, which actually means that there is a large current. Okay, and then now we will try another thing, but this time we will replace this light bulb with a voltmeter, because the light bulb doesn't really tell you about the direction of the current. And then if we have this voltmeter and look at their signs, you will see which direction the current is flowing. Okay, now first I will move this magnet closer to the loop, and then let's see where it goes. Okay, did you see? This needle tilted toward the negative direction. Okay, and then I take it away. Okay, so let's try again. So I move closer. Okay, it was to the negative direction, and move it farther away. Okay, it was the positive direction, right? Okay, so remember, the one thing you have to remember is that the positive and negative actually depends on how you connect the voltmeter. But anyway, the important thing is that when you move it closer or further away, the direction of the current or the direction of the voltage, polarity of the voltage was actually opposite. And then now again, try to remember that when you move the North Pole closer, it tilted toward the negative voltage. But then now let's flip the polarity and then move the South Pole closer. Okay, did you see? It actually tilted toward the positive direction. So when you flip the polarity of the magnet and then move along the same direction, again the direction of the current was opposite, and the polarity of the voltage was also opposite. Okay, so these are the observations that we have to explain. And the simulated experiments that we have just performed was originally done by Michael Faraday and also by Joseph Henley. So they are the people who showed that the electric currents could be generated by magnetic fields. Okay, so let's summarize what they have observed and what we have observed. So we have seen that the current appeared only if there is a relative motion between magnet and the loop. Loop means the coil, okay? And then we also have seen that when there is a faster motion, there will be a large current, okay? And finally, we have seen that when you reverse the direction of the motion or the polarity of the magnet, then current also reverses sign and flows in the opposite direction. Okay, so these are actually summarized in these four figures. Here, in the first figure, we move the North Pole closer to the loop, and then the current flowed counterclockwise. And then if we move the North Pole away from the loop, then current flowed clockwise, right? And moving the North Pole away from the loop was actually equivalent to moving the South Pole closer to the loop. So in both cases, the current flowed clockwise, okay? And then moving the South Pole away from the loop is equivalent to moving the North Pole closer to the loop. And in both cases, the current flowed counterclockwise, okay? So these phenomena where you use the magnetic fields to generate current is called induction. And you can also call it magnetic induction because this induction happens using the magnetic field. Okay. And the current that appears during this induction is called the induced current. And actually the current flowing means that the EMF is induced. So therefore, the EMF that appears during this induction is called the induced EMF. Okay. And finally, Faraday summarized this in his law of induction, that an EMF is induced in a loop when the number of magnetic field lines that pass through the loop is changing. Okay, can you understand what it means? Well, you can simply put it that it will happen when magnetic field strength is changing near the loop. But it will be more precise to say that it will happen when the number of magnetic field lines that pass through the loop is changing. Okay. And then why did he say EMF is induced instead saying the current is induced? In fact, it may sound similar, but there is a small difference. In fact, the current requires the wire. So you need a wire so that the charges can flow. But if you say EMF, it does not really need the wire. But even the space or the area where there is supposed to be a wire, something is already going on. and then current simply means that there is a wire for the current flow. So it is more general statement to say that EMF is induced instead of saying the current is induced. Okay, that is why. And in fact, one more thing I have to mention is that this Faraday's law is not an explanation of what induction is, but it is merely a description of what induction is. So it simply describes what Faraday have observed and what we also have observed. And we will explain the induction of phenomena called induction in a better detail in some of the next slides. So now let's use mathematics to describe Faraday's law. And in doing so, we need to define magnetic field flux first. And this is very similar to the electric field flux that we have studied when we were learning the Gauss law. Okay, so what was electric field flux? Electric field flux was an integration of electric field around certain area, right? So therefore, we have to define the area vector. And then example is shown here. In this case, for the magnetic field flux. So suppose you consider an area like this, which actually represents a loop or coil. And then in this case, the vector, area vector will be pointing perpendicular to the area, and this side represents the area itself. And then if this magnetic field is going like this, then we have to make a dot product, which means that only the component parallel to this area vector is useful. And then if this area is flat, we just multiply by the area. But if this area is not flat, then you have to integrate around this area. Okay, that's how it is. So this equation actually shows you the how you calculate the magnetic field flux. Okay. And then, what is the unit of this magnetic field flux? And in fact, do you remember what was the unit for the magnetic field? In fact, the SI unit of the magnetic field was Tesla. So therefore, naturally, the unit for the magnetic field flux will be Tesla meter square. Okay, and then for this Tesla meter square, we will use the symbol WB, and this is coming from German physicist name Weber. Okay, and then now finally use the mathematics to write down Faraday's law. And in order to do that, I will restate what we have seen in the previous slide using a little bit changed language, which can be interpreted into the translated into the mathematics. Okay, so what it says is that the magnitude of EMF induced in a conductive loop is equal to the rate at which the magnetic flux through the loop changes with time. Okay, do you get it? Here, the magnetic flux is actually the same thing with the magnetic field flux. Okay, and for the magnitude of the EMF, we will use the symbol delta V in like this. Okay, because actually EMF is a potential, right? So this potential appears across certain area. So therefore, we use symbol delta V ind. Okay, so let's try to write it down using mathematical equation. So I will do it this way. So this V ind, which is an induced EMF, is now equal to the rate or time rate at which the magnetic flux is changing. So therefore, I will take a time derivative of the magnetic flux just like this way. Okay, does it make sense to you? Okay, I hope so. And in fact, we noticed there is one thing we didn't expect, which is this negative sign. Why do we have this negative sign here? Okay, I will explain this in the next slide, so please be patient and wait for the next slide. Okay, and in fact, this area actually represents either loop or current, as I said. And if you say this is loop or coil, not current, okay. And if you say it's a coil, then actually you can make many turns of the coil, right? And then if you have many turns, then each turn will contribute to this induced VMF. And then, these turns are connected in series. So therefore, the total induced EMF will be proportional to the number of turns. So therefore, if you have n number of turns in your loop or coil, then you have to multiply n to the induced EMF, which means that if you have a larger number of turns, then you will have more or larger induced EMF. Okay. And so, using this equation, let's try to get some idea how you can practically generate or induce EMF. Okay. So, in order to do that, let's take the simplest example. So, let's consider the case you have a flat area which has the area A, and then this is at an angle theta with respect to the magnetic field direction, and then we can simply represent this magnetic field flux to be magnetic field multiplied by area multiplied by cosine theta. Okay, and then now we have to take a time derivative. Okay, so how do you take a derivative when there are many things together, multiplied together, and then all of them can be changing? Okay, in that case, you have to take a time derivative of each of them while leaving the other out, and then make a linear summation finally, right? So it's just like this. You first among B, A cosine theta, first you take a time derivative of the B while leaving the other two intact. And then in the second term, you take a time derivative of A while leaving the other two unchanged again. And then finally, you take a time derivative of cosine theta, so you get sine theta and d theta dt. Okay, and in that case, BA will be just left out. Okay, and then you make a linear summation. So does it give you an idea how you can create V in delta V in, which is not zero? It will happen when these or any of these terms are not zero, which means that you can change the field as a function of time, or change the area as a function of time, or change the angle between the area and the magnetic field as a function of time. Okay, these are the practical methods, and we will see real examples later.